I've just created a MATLAB script that does sampling for one die uniform. Here it is. And as every time I click the keyboard, it rolls the die 3 times. So you can see the green ones are the 3 rolls that you get, the 1, 5, and 6 in here. And this is a histogram, so the y-axis is the counts, and the red middle thing is the estimated mean. So once we click it a few times, this is with replacement. For dice, doesn't make sense to run it without replacement. So if I run it many times, we can observe that this is a uniform die, and that the average will converge slowly to 3.5, which is the average, theoretical average of the die. So now I've run this die about 500 times. That's in the sample size here. And we get an estimated mean of about 3.4 and the standard deviation of 1.68. So I could stop these it's running again, and roll. I have another die that I could roll that it's not a fair die. So here's another die that I'm rolling, and this die is it has more probabilities in 1 and 6s. So again, the green ones is the latest roll, in this case a 1, 2, and 3, in this case a 2, 4, and 5. Now it's a 1 and 2 6s. So if we roll this die a lot, we're going to observe the counts heavy on 1 and 6, which means this die is not a uniform die. But as it happens, it has uniform probabilities on 2, 3, 4, and 5, so the average is still 3.5, like on the first die. So now I've run this die maybe 500 times or so. It has a standard deviation of 2.09 empirical measurements, which is bigger than the first die because the values are farther from the mean. 1 and 6 on average are farther than the average of the first die, which could be any 1, 2, 3, 4, 5, 6. So now that we roll this die a few times, this program allows us to do quite a few things. In particular, we can roll the same die not 3 times at once, but say 10 times at once. So here's how that works. Every time we press the keyboard, we run it 10 times. So it's faster to get to convergence and large sample sizes this way with 10. Finally, I have another die which is heavy on the values 3 and 4. So let's run this die. This die is now we can observe it's heavy. It's likely to come up 3 or 4, and because 3 and 4 has the same average 3.5, we're going to notice that on this die also the average is 3.5, although the counts are again heavy on 3 and 4. So what you could observe here is the difference between 3 distributions of those die rolls, which are all have the mean 3.5, but the difference between these 3 dies, one of the differences, it's in the standard deviations. The bottom one has a smaller standard deviation or variance, which is the square of standard deviation, because the values are closer to the mean, 3 and 4. The middle one has the largest standard deviation because its likely values, 1 and 6, are farthest from the mean. And the first one is the uniform die, which is kind of in between standard deviation. Now I could also sample 2 die rolls to look at the sum of so here's a 2 die roll. It's a uniform die, so I'm going to move these windows out of the way here. On a uniform 2 die roll, we're gonna see more likely 5 and 6 and 7 and 8. In fact, 7 is the more likely one because there's more possibilities to obtain a 7 with 2 dice than it is to obtain a 2 or a 12. There's only one way to get a 2, that is a 1 1, and one way to get a 12, that's a 6 6. But there's many ways to get 7: 1 6, 2 5s, 3 4, 4 3, 5 2, and 6 1. So if we sample this now, I throw those 2 dice, I throw them about 1500 times. The mean is very close to theoretical mean, which is 7, and we get a standard deviation for the random variable, which is the sum observed of the two values, of about 2.43. We could also sample coins I have here, or cars, but what I want to show you is sampling. In this case, I'm going to sample midterm grades for the fall 2017. So I have here the grades, and I'm sampling 3 at a time with replacement. That means I put those exams back in the pile before I sample 3 more. Again, the green spots is what I sample. This is bucketed, although the grades could be anywhere from 0 to 100. The histogram here is bucketed in 20 buckets. So really, when you sample something, it counts as a unit for the bucket between, say, 70 and 75 or something like that. So if I sample here, you can observe the average being about 76, which is not as bad as students think it was. Most students think this was a heavy meter, but an average of 76 is not that bad. And actually, looking at the distributions, you can tell here that a lot of students did really well. The median was 78, but look at those high bars on 80s and 90s. Those are all like A minuses, B pluses, and so those this are not such a heavy meter. What I could do here is to sample 600 uniform integers instead, not the midterm grades, and that will be looking at 600 uniform integers. They're also like the midterm grades between 0 and 100, and it shows you uniform distribution with an average somewhere around 50. This is sampling 10 at a time. What I also can do here, I have set up, is to sample a bunch of integers like that, distributed in a different way. That is, they have the mean like the midterm 76, but they are not distributed like the midterm grades. Let me see, where is that one? I don't think I have it right here. So I'm going to run this experiment now. That is 600 uniform integers, mean close to 76. So how that looks like? There's still 600 integers. The average is still 76 like the midterm, but this obviously has a much smaller standard deviation, because this would represent a class of 600 students that all scored between 75 and 79. Look at those bars in there. No matter what we sample, everything is at 0.76, and you can observe this in the standard deviation here. The difference between those two distributions, one of the differences, is not just the shape. The bottom one is a Gaussian distribution, or normal. The top one is not. But you can tell in terms of difference to the mean, this is all crammed into the 75 to 79 range, a very small standard deviation, while the top one has the actual grades have a standard deviation of about 14. So that's what I wanted to show you. There's more options here in this script. You can do make it a little bigger. You can do the meet and grades right here. You need a file for that, the file with the meet and grades. That's okay, the file is public, has no names in it, just the numbers. You can throw in cost choices, coin tosses non-uniform or uniform. You can sample car prices. You just have to write the right command in the MATLAB console here, which looks like this, the command. So the three parameters: one is the task, one is the with or without replacement, and the number of samples you want every time you press the keyboard.